on-site wastewater treatment. And is that typically this involves, construction or installation of a septic tank, and then this passes the water into the soil media, and so the soil media is both a treatment and also a dispersal place for wastewater. We said again that the septic tank provides treatment, primary treatment, and the soil provides the secondary treatment. And by primary treatment, we mean that this is where the readily settleable solids are retained, and then the dissolved organics in the wastewater or BOD is then digested or stabilized in the soil media. And why do we call it septic tank? It is septic tank because it, just as we talk about like a septic wound, is that these also we exhaust. Remember, the septic tank is a reactor. It is confined. We said one of the things about a septic tank, it does not allow any water or any to go in or out. And that means then the only oxygen that comes to the septic tank is what comes in with the water. And so very soon this oxygen is exhausted. And so the processes that happens inside the septic tank are anaerobic. So a septic tank is an anaerobic treatment system. The process goes on without oxygen. And and that's where the issue of the septic comes in. And because it's septic, then the gases produced have a lot of methane. That is why the smells coming from, we have a lot of nitrogenous and methane products. And so when it comes out, then it is repugnant. And which also tells us that if then we keep holding this water for too long, then the only consequence is that we'll have smells that are not very pleasant. That's why when you have a very big septic tank that retains water beyond the period we discussed, 24 hours approximately, then you risk, you are actually enhancing anaerobic processes, and these anaerobic processes only produce gases. So remember, it does not benefit you at all. In fact, it works against you to have a septic tank that is very huge. As we said, ideally, septic tanks should hold water on average for about 24 hours. So I've seen certain cases where people saying, I want a big septic tank so that I don't have to it can last me for longer. That is not the case, because a septic tank does not hold water. It is not meant to retain water, it's meant to retain solid. It only retains water for a short period to allow the settlement of the readily settleable organics, solids. And from there, it proceeds for the next stage, which is where you achieve secondary treatment in the soil. And we said when we discussed last time that the trench is not deep. It is up about 600 millimeters, 2 feet below ground, so that there is the exchange of oxygen through the root zone of the vegetation that is available. So now, having said that, then we come to that there are instances where we have high groundwater, and therefore the moment you discharge water from the septic tank, it immediately start interacting with groundwater, and so it contaminates. So there is no provision, there is no room for good treatment. Second is where the soils are poor, but the soils don't drain as quickly. And the third one is where we have high population density. We discussed this and we said that population, that this, remember when we talk about the banana peel, and we are saying that the problem is that when that environment has a carrying capacity, and beyond a certain capacity, it cannot sustain the pollution load. So if we had only 10 houses in Juja, that's fine. But when we start having these high rises and all that, each of them holding, 50 people and so on and so forth, then for a given area, quarter an acre, we have so many people discharging it with the soils cannot actually take that volume of water. And so we start working on that. And so these are three areas that are particularly problematic when it comes to wastewater, on-site wastewater treatment, that where the groundwater table is high, where the soils are poor, or where the population density is increasingly high. So then we ask ourselves, how do we then treat the water that is coming out of the septic tank? How do we achieve sufficient secondary treatment systems? And so that to keep our goals that we said, we want to protect public health. We discussed this in our lecture number 1, to protect the environment. And then we find that the soils cannot achieve sufficient treatment. Just give me a minute. So then, therefore, how do we achieve this when we don't have, good, the soil is not sufficient to achieve good treatment? And so what we do that we resort to aerobic treatment systems. And the aerobic system, as we know, proceed much faster compared to anaerobic. And because then when we inject oxygen, we enhance the activity of the microbes. And so the processes of stabilizing, and by using the word stabilizing, remember why, we are talking about an activated, sludge or activated wastewater, meaning that there is active microbial activity. And this will continue until all the oxygen, or all the organics have been exhausted, or rather they have been stabilized to a level. So that process, that's why we talk about stabilization ponds, because we are stabilizing the organics. If you look at cow dung, for example, when it is fresh, it will get some worms, and they are active, they are digesting because there is food in it. But when they have exhausted, it becomes humic. And it is stabilized now. It is become manure. So this is the whole thing about what you're trying to do here, is a stabilization of the organic matter. And so oxygen injected or introduced into the wastewater enhances the microbial action. And therefore, it means that by the time we are discharging this wastewater, we have indeed reduced both the BOD and also the suspended solid, because what happens then is that, remember we say that the BOD is dissolved organic, so it is not readily settlable. So the microorganism in the water consume it, it becomes part of their body mass, and therefore when they die, when the microorganism dies, then it has accumulated. So you can think about it as a biological flocculation. You have brought together many small particles into one bigger mass that can settle readily. And so that settle to the bottom, or to the wherever it settles within the tank. So therefore, in that sense, we reduce both the BOD and suspended solids. Of course, because of that process of introducing air, you have pumps and so on, then there's a risk. There's also the other part of it, that you require more regular maintenance, additional maintenance, and of course that results to additional expenses. We discussed this already, that the typical, remember actually, and I think I've put this in the introductory notes to the lecture, that we are not changing the functional operations. It still remains the same treatment, and we discussed this last time, that basically we are using the two basic treatment, actually three, either attached growth, suspended growth, or lagoons or pond processes. They're the only three. We are only now tweaking them to achieve operational efficiency. That what would have taken 4 hours now takes 1 hour. What would have taken 21 days, start taking, we can achieve that within 14 hours or so. Now, or whatever time, typically you find that these treatment schemes, packages, will manage wastewater within between 8 and 16 hours or so. So that means you can process a higher volume. The throughput is higher. But the basic systems, the basic processes remain the same. Attached growth system, suspended growth systems, and also there are these treatments or derivatives of this. In case of suspended growth, you have what you call the extended aeration, or the sequencing batch reactors. In case of attached growth, we still need a media. There's a sand filter, a biofilter, geotextile, what you call the RBC, that's rotating biological conductors, or moving bed reactors. We'll see a little bit about these as we go. Right. So this is just one typical, this is just, one of the media and how water is distributed. And you can see then that other than using the trenches, one uses a bed, a sand bed with a distribution system, and on top of it, then you can even skip it. Of course, deliberately, it is fenced off, just to ensure, you can see that fence there, just to ensure that the vehicles don't park on top, because they will compact this media, and it becomes impossible for it to play its part. And of course, you see now that from the sand, they even have a smaller media, where now we use geomembranes, geotextiles. So this again now is a modified. So the same theory about an attached growth service, but using the different materials that are available, and sometimes that we achieve higher efficiency. Of course, we know that the more we can create the attachment surface even much more. And even in some cases like that, you can even have what you call the biofilters, like this one. You just basically a tank filled with sand, and therefore you can manage. So within a limited space, then we can continue considering, but the basic processes remains unchanged. Now, if not using the same biofilter, you can see there's what we call the foam, the open cell foam, and now you have the this foam material. You can see it inside there. Yeah, you can see all this. So instead of a sand now, you can so just saying what material is available to us and how do we deal with it. And of course, these then can combine. You definitely know about the wetland system, and so you can the constructed wetlands. And so again, it's a sad media, and then with planted vegetation. And you can see then after that, it becomes a beautiful garden. And so it uptakes the nutrients. It is, and that's why I think that actually advanced wastewater treatment supports the recycle and reuse of wastewater because we are treating water to a higher standard than you would achieve with a septic tank. And so in this case, then the water is being used for landscaping. But in other cases, it even be used for flushing and such like functions or uses. So that, but let me speak specifically. So let me say this. Advanced wastewater treatment can look at two core parts. Remember we said, what does the soil do? It treats secondary treatment. It achieves secondary treatment, but also disperses. And you'll see that the methods that we use for what we call advanced is either about secondary treatment or about improving the dispersal. But I want us to pay a very specific attention to the aerobic systems. Give me a short break. Just give me 2 minutes. I think I may get off the class a little bit early. I think my body is not behaving too well. But let me see how far I can push it. Yeah, so we're seeing that then with the aerobic treatment systems, what we are doing is that we are injecting air or oxygen, and then through various methods. Sometimes we use service aerators, sometimes we use the bubble, the diffused air bubbles, and so on. But whichever way, sometimes we use a mechanical agitator. So all these are possible ways that we can use to introduce oxygen into wastewater. But as saying, the most important thing is that we are encouraging aerobic processes to subsist. And so typically then is that you have a septic tank that serves almost all advanced wastewater treatment include a septic tank or a primary settling tank. After that, within the water that is, lesser or has less suspended matter, but still high in BOD, then go to an aerobic treatment unit where then the air is introduced. In some cases, you may have a disinfectant introduced, and then you have a clear water storage tank. Or in some cases, you push this through either for irrigation or for other uses. So that's what basically we have. Now, and that's the same thing that we are doing in this what is it called, in this diagram. Let me just show you another picture which I think perhaps illustrate this better. Yeah, so what you have there, you see then what happens is that, so the wastewater comes in just around there to the primary settling tank, then to an aeration. Of course, as I'm saying, you'll have a whatever system of aeration. So you see the aeration chamber, and then you allow some settling. Now you see this pump here at the bottom, what we call is a sludge return. Two things can happen or will happen. One of them is that you'll have a small proportion, approximately 30% of the sludge returning to the first chamber to introduce what we call an activated sludge. You remember we said that one of the very important design parameters in wastewater is what we call the F&M ratio, the food to microorganism ratio. And it just goes, I mean, you think of it logically, is if you have one person with the 30 loaves of bread, then it goes without saying that the loaves of bread will start going stale before he can finish them, unless he has an economic capacity. But then when you introduce 2, it takes a shorter time. When you introduce 10, then it becomes easier to share. If you get 30 people, then within hours, the loaf of bread is dealt with and finished. So in a similar way, we have a lot of food in the name of dissolved organics that is introduced in the chamber at the inlet. And so we need, and initially there's only a few hundreds or thousands of the microbes. So you bring in active, mature microbes so that then they start digesting this very soon. And that's how we end up now achieving a shorter period. So as we see the sealers, you have increased the population of the active microorganisms at the start of the process so that you don't have to wait for the natural regeneration. But of course, at the same time also from the settling chamber, we said we are only recycling about 30%. The other 70% is then wasted. So we call it it's a wasted sludge. So we remove this. Because again, if we do not do that, or if we are to recycle everything, it means then is the opposite will happen. It's having one bread being shared by 100 people. And what it means that these people will actually starve to death. So likewise, when the wastewater has been deprived and of the organics or the food, then the microorganisms start to die. So it is important to achieve an optimum number or an optimum ratio of the microorganisms to food ratio. And that's one of the very, very important design parameters that we consider when we are designing this kind of systems. So back to the settling chamber. So then there is a sludge that is removed, or we say it is wasted, because again, the settling, remember, and I think this is one of the assignment, Harriet, you need to frame the question and share it with the class. It's one of the assignments we were to do, and we said that depending on the density of the solids, the settling regime changes. So we're having very high density of micro solids there, then becomes not very good, and so we waste some of it to also attain a certain ratio. And then of course the other chamber of disinfection and what have you follows. So that's just a schematic view or diagram of an improved wastewater or an advanced wastewater treatment scheme. So back then, the lecture, let me see. The question here, the treatments covered here, not bring water back to. Humphrey, I hear your question. Yes. Remember the the easiest of ways of reusing water, and as you see in the next topic, it is landscape irrigation. Because one of the things is that water contains nutrients. In any other form, the nutrients will be contaminants. But when it is used for irrigation, then it's actually beneficial. So you'll see that irrigation constitutes the largest user of reused water. But remember, even for normal abstraction, basically irrigation constitutes 70% of all the world water consumption, even fresh water. So that also becomes another incentive that actually people are needing water for irrigation, and this doubles by the fact that this water also contains nutrients. But as you come to the next topic, which is immediately after this one, we will be looking at what does it require to reuse wastewater for other uses beyond irrigation, in fact, irrigation and others. And what are the constraints, what are the advantages, and what are the disadvantages? And that's where we'll look at it. So what if you're using it for vegetable? What if we're using it for other beyond landscape? What are the risks? Remember, we are still about managing public health risk. So by using wastewater, and we'll come to something we'll call either restricted or unrestricted use, and we see for each type of use, what is the quality standard required? And of course, the higher the standard required, it means the higher the cost of treatment. So that will be our second topic. So if you can hold those questions, when we come to the next topic next week, then we'll see that yes, Jogu Stephen, yes, wastewater can be treated to drinking standards for potable purposes. It can be, and actually in some cases it is. But remember, beyond all things, there are also the social perceptions. So that has been one of the biggest inhibiting factor towards use of water or wastewater for drinking. That just the social perception doesn't go very well. In fact, even for very many people, even if you have treated the water and even you have disinfected, and someone know that you have grown the vegetable, for example, fruits, sukuma wiki, and all that, using wastewater, even if you assure them the water is clean, people will still be, apprehensive. But you'll also see other things that we see that beyond the organics, there are also the risk of what you call the rare pollution, or things like mercury, zinc, all those kind of things, that kind of pollution, or what you also things that we call persistent organics, then it's a different story altogether, and this also requires a due consideration, and we'll see that when we come to the next topic. Allow me to proceed a bit, and I think this is still one of other system. I think this is what we call the buffered reactor, which allows water to either go, if you look at this part here, it goes down, comes, it's that series of things. Or there is also the one that we call is, you can also have the same, and you have this kind of an arrangement. And so that then wastewater then goes around. So it's called a buffered anaerobic ABR, anaerobic buffered reactor. So it can go horizontally around the buffers or can go up and down. It's, like you have done here, shown here. So both of them are valid. So that's also a system. It lengthens the time, and and you also have a more controlled environment. So, and so you subject water to these different conditions, aerobic and anoxic and anaerobic, And each of them, then you find that when you have anoxic conditions, as you have done in the previous courses, then it's helpful in terms of the identification and so on and so forth. So long and short, the same systems. So let me just say, when then you use anaerobic systems, why would you do that? First of all, they are very stable systems. They are not very prone to shock, for a simple reason that they tend to have a longer detention time, and therefore they can absorb the temporary shocks in inflow much more easily as compared to aerobic system. Two is that it produces methane. You know, if you want to do biogas, you don't get biogas from aerobic. You can only get biogas from anaerobic systems. So don't try, if you are trying to, if you use aerobic system and you're trying to capture that gas, what actually you get is carbon dioxide. So if you are intent that your system should also give you biogas, then by rule, you must apply an aerobic treatment scheme. Of course, it also produces less sludge. Remember what we said, that the reason why aerobic system works faster is because they also encourage high rate of regeneration of microorganisms. So they get born and they die. And therefore that means it produces much more sludge compared to aerobic system. Then because you're not having, you don't have the high regeneration requirement, then it also means that you don't need that many nutrients. So water that is not very rich in certain nutrients, then it is better to use aerobic as compared to anaerobic, rather, when the water has low nutrient levels. You don't need water. Then, so basically speaking, anaerobic systems are very good for strong. You remember we talked about low strength, medium strength, high strength. And so basically for any wastewater, 450 milligrams BOD and above, then I would automatically seek to use anaerobic systems than aerobic. But for the conventional domestic, the anaerobic systems works very well for you. The disadvantage is that it takes a long time to start up. You know, it should have sufficient alkalinity. You need a bit of temperature there, and then nitrification is not possible. Remember, we talked about the anoxic conditions. This means it's a time between aeration, and then you give a bit of quiet time. So, but this one, because there's no aeration, then it's not possible. So you still get a lot of nitrogen and phosphorus at the end. It's high, of course, it's very much dependent on the ambient conditions, and then, of course, not very good when you have very high CODs, and that, as we talked about, that the effluent from anaerobic processes are generally not acceptable for discharge. So we still need to do some bit of polishing. So anaerobic processes are good in one part. They have a limitation in another part. So, and so for, you know, this is now a scheme for aerobic. I think we have discussed it, whatever. And we said that, you know, an aerobic reactor, which oftentimes is a septic tank, and so on. So aerobic tanks has many forms. These are some of the, and I should discuss this later, maybe about the processes and the methods. You see, these are technology, but the process, we say there are only 3 processes, but out of those 3 processes, there are many technologies or methods. It's like you say, look, if you want to make make bread, all of them have a basic process that you're going to bake. But you can make this bread to be twisted. It can be the rectangular bread. You can add a bit of, you can make it oat bread. You can add some bit of seeds. You see, but the basic thing, it is bread. It is bread and it is baked. But the methods, the duration, the additives are different. So that is what it is, that all these, the three basic process, activate, suspended growth, attached growth, and lagoon systems. But in between, there are variants that happens, you know. So what is said, doesn't be the process stability. The stability of the process means that the effluent quality is more stable. Now, simple reasoning. Here is wastewater that is retained, say, for 7 days through the treatment tank. Here is another one that is being passed through 4 hours or 8 hours. What it means then, if you have designed this for an average of 100 cubic meters per hour, and then within 2 hours there's an upsurge where you get 170. If the total detention time is 8 hours, then you'll feel the effect of that surge. But if the effect is 7 hours, then 2 hours out of 7 days rather is nothing. So that's where the stability is coming from, that it produces a more consistent product. So it is easier to design on average basis using an aerobic, but when you come to aerobic, you need to consider to have factor in the peak flow. In fact, the peak flow may play a big part in your decision in sizing the facility. So that's your response, Julius. Now, so that's where we are. Allow me, people, I have to stop there. I just can't push it any further than that. I really apologize. I'll be in touch with Harriet to see when we can carry on with this class. Because I would like to discuss this when I'm also have a bit more energy. So sorry about that. Harriet, I'll be in touch with you about the class assignment. And thank you, everybody. Enjoy.